Okay, so welcome everyone. Welcome to this month's edition of Flower Monthly. This is our October edition, and we just want to say welcome to all those who are joining us in person live, and also everyone that we're seeing watching this on our YouTube channel in subsequent opportunities. It's fabulous to be back with you. We have a really interesting Flower Monthly, I believe, this month. What we're going to do is give you a few updates of notable events within the community and the framework that's happened over the last 30 days. And this is our kind of normal way of warming things up. But after that, we have two fantastic speakers, and they're with me here right now. The first invited speaker after we've given these updates will be a talk given by Solomon Githu, who produced a tutorial on how you can use IoT devices in a federated learning setting. And so I saw this tutorial that was publicized by Edge Impulse because he's a contributor to the Edge Impulse expert network. And I couldn't help but notice that the federated learning framework of choice in this tutorial was Flower. And so, of course, I couldn't wait to reach out to Solomon to see if he had the time to show us some of this material and walk us through some of these techniques to all of our community. So thank you, Solomon, for joining us for this first invited talk. After Solomon, we are going to have Kwangkee Lee. He is a principal investigator at InnopiaTech. And I do apologize if any of those pronunciations were not completely correct. But he's going to talk to us about an equally important and fascinating topic, and that is how blockchain and federated learning can be melded together in an architecture and for it to enable some really powerful federated learning applications. And so we're also delighted to have him here with us today. So with that as an agenda sort of broadly outlined, let's give a couple of Flower updates. And with these Flower updates, we often like to review what's happened in the past month. And so I decided it would be appropriate to review one event that happened on a Friday. We've been experimenting with a few different community events in the last few months. We had Flower Around the World. A few months ago, we had our annual event of Flower Summit. But in this last 30 days, we had an event we called Flower Friday. And this was a live update that was focused on the capabilities of the framework to provide enterprise grade features and capabilities that we'd seen being used by various organizations of different sizes around the world. And so this was a session that happened on Friday evening, at least in the UK, where Daniel, one of the co-creators of the framework, walked us through initially a number of the enterprise scale use cases for Flower that we've been seeing. And so we're often very surprised to see just how widely Flower is being used in a variety of different types of organizations. And so in this session that you'll have available, I think, on our YouTube channel in due course, there was a series of examples given how, for example, Brave, the privacy-oriented browser company, has been experimenting with Flower as a framework to enable various types of federated learning applications. He also went through, for example, Banking Circle. This is a B2B bank that does 10% of all the transactions, I believe, in Europe, who have been also experimenting and now going very close to production on using Flower to enable a system they call Flame, which does anti-money laundering. And Daniel also mentioned a few other use cases that maybe people haven't heard of so much. So one of these being Bosch. Bosch has an open source multi-party communication software stack called Carbine, and they've invested quite heavily in combining Carbine and Flower. And finally, he mentioned some of the kind of really interesting use cases that we've seen come out of the Air Force, largely in the domain of education, but also when they do more forward-looking aspirational considerations of where ML might be used. Federated learning does appear to be kind of rising in their kind of expectations. And so that was sort of some of the main content of use cases were provided. And then Daniel gave us an outline of some of the increasing capabilities of Flower to service enterprise users. So he was talking about one of the main drivers of this is Flower 1.5. It's a very recent release. It has a suite of capabilities that we find aligning really well for enterprise scale usage. So I can't really go through all of these individual capabilities, because actually when we added up all the different PRs that are included inside 1.5, we realized that there were more than 232 PRs. So some small improvements, some large improvements, but across the board that deliver on a lot of capabilities that enterprises need. And these range from the new simulation engine that's much more stable, scalable, and is efficient in resources like memory, a wide range of improved support for mobile device clients, particularly in the direction of iOS and new forms of Android, powerful documentation. And then a lot of that Flower Friday was on this topic, as well as describing what is coming next. And so again, if you're interested in this sort of content, you should check out this video that will that you better find shortly out there. And so in terms of enterprise capabilities are more upcoming, he was talking about how we have official Docker images that are often very enabling for enterprise scale rollout that are available from this month, and also the advances in the Flower Next migration. And so while Flower Next is offering key advances such as the driver API, it's previewed in the current 1.5 version, but being made stable in the upcoming months. And so there are dozens of other types of capabilities that really focus on enterprise usage. And so there was sort of also a sketch of the roadmap, talking about the driver API, how it's used and how it becomes stable in Flower 1.6, a very ambitious set of technologies that we're combining and calling FedGPT that enable Flower to train LLM models, and many more. But before I close the section of Flower updates, I do want to pinpoint one other capability that we announced on that Flower Friday that is going to appeal not only to enterprise users, but also the wider community of Flower users that include researchers, folks involved in R&D and proof of concepts in companies and so forth. And this is an important step forward in even federated learning in general. And it tackles the thorny issue of federated learning data sets. It's well accepted that federated learning is being held back by the immaturity of many of the data sets that we have available to us when we experiment and test and develop. And so during Flower Friday, we had a fantastic part of the Flower team, Adam, who's been the driving force behind Flower datasets, announced this feature as somewhat of a surprise. And so Adam essentially outlined for us the heavy lifting and error-prone practices that currently go into the preparation of Flower datasets, of federated learning datasets in particular. So it doesn't matter which framework you're using. If you want to do a federated learning experiment, you have to go through a series of manual steps whereby you find the dataset that makes sense for your experiment or your proof of concept. You have to download it. You need to partition it in a way that makes sense. And there's many of these manual steps. And we found, talking to researchers, engineers, that they were all repeating all of this work, and it was causing not only a slowdown in the speed of the work, but also errors. Because a lot of this work, if you get it wrong, can really skew your results off dramatically. And so Adam outlined the sort of the manual labor that is behind the problematic use of datasets today, where everyone is doing it themselves. He highlighted how there was a lot of error-prone code. There was a difficulty on being able to reproduce results, and because of the way that datasets were being handled in an ad hoc fashion, not within frameworks, it was very hard to port a data set from one architecture to another or from one framework to the next. And so, as Adam explained, we are hoping to make this a thing of the past with this new capability of the framework that we call flower datasets. And so flower datasets is able to be tested and explored in its preliminary release with just one line of code. You can trial it out today. We think that it offers some key capabilities. We also believe that these capabilities are going to be advanced strongly in the coming weeks and months, because this can be an important game changer for the speed and efficacy of the results that we can get from federated learning as we start to develop them. And so this new approach to release data sets within our framework is going to mean that when you need to use data sets in your code, the amount of code you have to write yourself is vastly reduced. Many of the boilerplate techniques, such as the downloading, the partitioning, the interaction with the framework, all of these things, to the degree that's possible, are going to be taken care of for you by flower datasets. And you're going to be presented with some very clean abstractions that are well documented, that are easy to follow when you need to be able to take this data set that's available in our framework and apply it to the setting that you need. And so not only does it sort of nail many of these sort of problems that currently exist in the way the community uses data sets, it also provides a host of additional benefits, such as you can have a suite of various kinds of partitioning schemes available out of the box. You might want to partition based on user, based on some sort of mathematical function that is predictable and repeatable. It's really very easy to integrate the Flower dataset code, obviously, with other capabilities of the Flower framework. And we've specifically considered how to minimize the difficulty of migrating any existing federated code that uses datasets in a different way to this new set of datasets APIs. So really, I'm just sort of trying to sketch out for you this capability. You can look at the sort of emerging Flower datasets documentation or the video when it's released. But that is the Flower updates for this month. It's focused a lot on the singular event that we call Flower Friday, where we discussed in detail, first with Daniel discussing the capabilities of Flower and how they align with enterprise use cases and the adoption that we've seen already. And it was sort of tail end by Adam announcing the exciting and powerful capabilities of Flower datasets that will be important to enterprises, no doubt, but also of high applicability to the entire Flower community. So with that, I'm now going to transition to our first invited talk. And so this invited talk, and it's going to be, I think, in a more of a tutorial sort of nature, is going to be given by Solomon. Solomon Githu is a contributor for the Edge Impulse Expert Network. And Edge Impulse has done amazing work over the last few years in democratizing and spreading the word of TinyML and edge IoT types of capabilities. And I think the tutorials that they've released have been fantastic. And so I was really quite interested when I saw Solomon's tutorial on federated learning, where he showed how you can use things like Raspberry Pis under a federated setting. And of course, it really warmed my heart to see that the framework he used was that of Flower. And so I couldn't wait to invite him to speak to you all. So Solomon, thank you so much for joining us today. I'm happy to hand the floor over to you and see what you have for us this evening.
Hello, thank you very much. Let me first start by sharing my screen. I hope you can see my screen.
We see a PDF, looks a little bit zoomed in, and now it looks perfect.
Okay. Thank you very much, Flower, for inviting me to this talk. My name is Solomon Muhunyo Githu. Currently, I'm in Nairobi, which is the capital city of Kenya. I work as a researcher in a company that's called Wazia EV, and we major on LoRaWAN IoT applications and also AI. I'm also active in the machine learning space, and I contribute to the Edge Impulse Expert Network. And I started machine learning some few years back. I used Edge Impulse platform and some open source platforms to learn how to do it. It's a very complicated field, but with these AutoML tools, it makes things easier. And so one of the things that I realized is that there is a problem, or there is a limitation when it comes to centralized machine learning that we do. And that's where I realized that federated learning is there. And I did some digging, I did some trial with some various federated learning frameworks, and eventually I landed on Flower, and I am decided to use it because it's very easy, it's very flexible, and I also like the tutorials out there that enabled me to finish this project. So to start with, I want to talk about the classic machine learning workflow that we do. So if we want to train a machine learning model, the first thing that we do is to prepare some data sets. And this data set, it can be audio data, it can be images, or it can be maybe a CSV files with your data. We then take this data and then we train a model. For this training, we normally use high performance computers that can do this training for us. So we take the data, we put this data in this computer, and we train a model on this computer. After we train a model, we then need to validate the model. So we do a test on the model and see if the model has learned well. If the model has learned well, then we go to the deployment phase where we can deploy this model. Let's say we can deploy it in microcontrollers, like the Arduinos, the Raspberry Pis. We can also deploy our models on computers such as mobile phones, and even personal computers. Uh, and this is the workflow that most people are used to. And even this is the workflow that I've been doing for a long period of time. But then there is some challenges with this centralized approach. The first problem can be data, and data can be sensitive. So if you decide to use the centralized approach, you need to collect all the data from various computers, and then you, let's say, send it to the cloud. If the data is sensitive, maybe it's financial data, you don't want to send financial data to the cloud. Um, the other problem is diversity of data. Um, Normally, we tend to take data from specific sources. So you may have, let's say, one computer that is taking the data, and then you take that data, you put it to the cloud to train the model. The problem with this is that the data, it's not diverse. If the data set that this computer is collecting, if it's not diverse, then it means that the final model that you'll have, it will be biased in one way or another. So diversity is a huge problem when it comes to having just one centralized data. The other huge problem is the quantity of data. And if, let's say, for example, you have an IoT device, let's say like a Raspberry Pi, which is collecting images, and you want to train a machine learning model, let's say to identify if there's an elephant in an image. The problem with the centralized approach is that your Raspberry Pi will need to collect maybe 1,000 images. Then you decide to use a cloud computer to do the training. So you take these 1,000 images, you send it to the cloud to train your model. The problem with this is that if you don't have, let's say, good internet access, um, then there is a problem. So you can't do the actual transfer of the images files to the cloud. And so that's where now the idea of having a decentralized model comes. A good example of a decentralized model is, let's say, our mobile phones. So if you have a mobile phone, you take it and you say, hey, Google, hey, Siri. Your mobile phone, it can detect these words. Your mobile phone, it also knows how you look. If I take my phone and I look at it, it can unlock the screen because it knows how Solo looks and it knows that Solomon is a person. Um, the problem here is how do we get these models? How do we get a model that can take a picture and say, this is a person and this is Solomon? Um, if you think about it, one of the things that we can do is, let's say on our mobile phones, we continuously collect audio data and let's say images. And then we take these images, let's say and then we send it to Google. So Google can do the training for the machine learning models with various data that comes from my phone, that comes from Alan's phone, that comes from John's phone. The problem with this is, again, we're taking data from our mobile phones and then we're sending it to the cloud. And our data is sensitive. And there is a lot of data that Google will need to push from our phones to the cloud. And that's where the federated learning approach comes into place, where maybe you have sensitive data, or you don't have diverse data, or let's say you don't have good um, uh, bandwidth to, let's say, in IoT devices, you don't have good internet access. So basically, in federated learning, instead of taking the data, the model, we take the model to where the data is. And in this demonstration, we will use one Raspberry Pi, and we will use my personal computer. So we have two devices. Um, the first device, the Raspberry Pi, and my computer, which is the other device. They each have their own data that they are storing locally, and each device will train a model. After training the model, there is a server um, that facilitates this training. So each device will train a model. Um, After each computer trains a model, it will send the updates to the server. The server will get different updates from the different computers. It will aggregate the various parameters that it gets, and then it will come up with a final global model. And then we can take this model and maybe we can send it back to each device, or we can send it to, let's say, a cloud server, so that any device that was not in this training process can download that model and then use it. So for demonstration, we will train an image classification model that can take a picture and it can tell if there is a head or if there is a heart in that image. So our machine learning model, it will look at a picture, this picture on the left, and it will say, is this a head? Or it can look at another picture like this one on the right, where the person is wearing safety hat, and it will say if this is a hard hat image. Um, for this demonstration, the use case of the challenge here is, let's assume that we have a construction site. And in this construction site, we want to create a system which can tell if the workers are wearing their safety hats. So we can use computer vision to do some surveillance on the workers, and it can say if it only sees a head or if it sees a hard hat. If it just sees a head, and since this is a construction site, it will, let's say, create an alarm, and then the supervisor can go to the person who was just seen with their head. If we decide to use the centralized or the, let's say, traditional machine learning approach, what we will have done is, we have security cameras in construction sites, and each security camera is taking some images or some videos of the workers at the construction site. It takes those images and then it, let's say, uploads it to the cloud. In another construction site, let's say number two, you have the same thing. You have a camera which is taking um, um, videos and images of the workers, and then it's sending it to the cloud. The problem with this is we don't want to send workers images to the cloud because this is sensitive data. And again, if we decide to, let's say, collect video footage for an entire day, and then we decide to send this footage to the cloud, this footage will be so long, maybe in terms of gigabytes of space, and we will need a lot of internet data to send this image to the cloud. So the challenge here is, what if in each construction site, the security camera that's there, it can take the images of the workers and it can train a local model. So it's taking images of the workers and it trains a model to detect if there's a head or if there's a hazard. In construction site number two, you have the same security camera, which is taking video footage of people and it's training another model. Eventually, these surveillance cameras, they can talk to each other in one way or another, and they can share the different models that they have trained. And these data or these updates will go to the federated learning server, and this federated learning server will then take the final updated model and will send it to Edge Impulse. So there is a project write-up for this demo project that's in Edge Impulse Expert network page. It describes all the technical details, all the choices that were made uh, regarding the realization of this model. So for demonstration, what we will do is, we will use one Raspberry Pi and my personal computer to train a image classification model. And this image classification model, it will take an image and it can say if it sees a head and if it sees a heart hat. And this model will be trained both on the Raspberry Pi and also on my computer. On my computer, I will also run a Flower federated learning server. And this server will facilitate the federated learning system. One of the challenges that I realized when it comes to federated learning is, how do you come up with this system? So in federated learning, you have different devices. Each device is training its own model. So how do you come up with a system whereby the devices are um, connected together? So a system whereby the server, you have like a server. The server, it can, let's say, initialize a model. It can take the initial model parameters. It sends it to each device. Each device, it will take that model. Maybe it's a MobileNet V2 model. Maybe it's a YOLO V5 model. It updates that model locally. After updating that model, it goes back and tells the server, I have this new model parameters. Another device will also tell the server, I have this new model parameters. The server will then aggregate those model parameters and it will come up with a final model. So if you think about this system in a technical way, it's very complicated. in terms of how can you actually do that. And this is actually why I loved Flower, because it's very flexible, it's very easy to use, and the uh, tutorials out there are really helpful. So we'll have a Flower Federated Learning Server, and this server will facilitate training image classification model both on the Raspberry Pi and on my PC. After the federated learning system, the federated learning server, it will then take the final model and it will send it to Edge Impulse. Now from Edge Impulse, we can then deploy this model to any device. So like for the training, we were training the model on the Raspberry Pi. But if we decide, let's say we want to add, let's say a JSON Nano to the um, um, construction site, we can easily use Edge Impulse, because Edge Impulse, it will store final model, and we can then deploy this model to any device that can run it. So this is what we will do for this demonstration, and we will run the and then finally we will run the model locally on the Raspberry Pi using Edge Impulse. So now I want to um, go to the code that I use for this. It's not very complicated, but I will simplify it. So we need two things, or we need three things to do this federated learning. So we first need a server. I use Python to um, do this federated learning system. So I have the first Python script. So this is the server script. We also have the client script, and we have the dataset. So for the server script, here we do the importing TensorFlow, OpenCV, etc. And then we'll also use Edge Impulse Python SDK. And I will show you the use for this SDK as we go to the code. So here I have the server address, and the server address, this is basically the address of my computer, and I'm running it, and I will run the server at port 5050. The other thing that we need to do is we need an API key from Edge Impulse. So what I can do is I can um, go- so I can go to Edge Impulse, and then I can create a new project. Uh, so I can call this flower. Let me call this project Flower Monthly. Then now I have a new project in Edge Impulse. Note that to create a project on Edge Impulse, you first need an Edge Impulse account, which is free for all developers. So once I have my Edge Impulse account, I can go here to keys, and then I can take my API key. So it's this one. I can right click and then I click copy. Then I can come here and then I paste my API key. Afterwards, here we will define an executable, which I call modelfy.eim. I will talk about this executable later. Here we define the classes for a model. So a model will have two classes. One class is head, the other class is heart. The other thing that we need to configure is the image size. So here I'm using an image size of 160 by 160 pixels. And this image worked well for me. Note that there is a trade-off between the image size and the performance of the model. So in some cases, if you use a smaller image size, it will mean that your model, it will run much faster, because a smaller image means that there is less data for the computer to process. But if you have a smaller image, it means that you have less data inside your image. So in some cases, depending on the number of objects or the features in the image, you may need to choose between having a larger image size or a smaller image size. But in this case, 160 by 160 works very well for me. The other thing that we need to configure is the federated learning counts. So here I set 6. So what this means is that the Raspberry Pi and my computer, they will be training a model 6 times. So the first time they get initial parameters from the server, then they train a model. After training the model, they talk back to this federated learning server and they tell the server these are the new model updates. And that process will continue 6 times. Uh, the other parameter is the number of epochs. So epochs is the learning rate. So this parameter, it tells how many epochs does each client um, have. So remember, let's say for the Raspberry Pi, it's training a model, machine learning model. So it will train that model 20 times for each federated learning count. Then the other thing is the batch size. So in this case, a batch size of 8 works very well for me. And then now afterwards, we go to the main function. One thing that I liked about Flower is that it enabled me to try out various models. In this case, so here I load a mobile net V2 model, but previously I also used an efficient net B0 model. When it comes to machine learning, different models have different performance. So in this case, you can see over here, like for the MobileNet V2, it has a smaller footprint, so it's just 14 MBs in size. It also trains much faster, and also the inference is also much faster. So that's why I settled with MobileNet V2. But in this use case, both MobileNet V2 and EfficientNet V0, they both achieve the same performance. But I decided to go with MobileNet V2 because it was much faster when it comes to training the model, and also the deployment part is also much faster. The other thing that we do here, so we load a MobileNet V2 model. Here we freeze the layers so that they don't get updated. So what we will do here is we will do transfer learning. So we have a MobileNet V2 model that has been trained on a couple of objects. So what we do in transfer learning, we don't train the model again. We just update the um, model parameters on new objects or new features that we want it to learn. So that's why here we are freezing the layers of the model so they don't become trainable, but we will just update them. The other parts of code, basically, they define the layers of the model. And here we are using Keras. So here we create the model, and then here we compile the model. So here we will use the Adam optimizer. Loss will be sparse categorical cross entropy, and then for the metrics we will be using accuracy to check the performance of the model. And then here we start the federated learning server. So this is just the uh, Flower way to start the federated learning server. So one of the things that is unique in this demonstration is that we will use at least 2 minimum clients. So for this federated learning to start, we need at least 2 clients. So the Raspberry Pi will be one client and my computer will be another client. So when the 2 clients have connected, that's when the federated learning will start. And here we pass other configurations for the server. One thing that I did for this federated learning, you remember in federated learning, take the model to the data. We don't take the data to the model. So for our data set, I created individual data sets. So we have the Raspberry Pi and we have my computer. So the Raspberry Pi, it will be one client, and then my computer, it will be another client. So for each client, we have different data sets. Because in a real scenario, if you have different devices, each device will be collecting its own data. So on the data set, we have different folders for the data set. So we have one folder for the first client data set, and it has both training images and it has both um, testing images. So if we go, let's say for the training images, we have two folders. One folder is hard hat, which has the hard hat images. Then the other folder is the head, which has the uh, head images. So we have two data sets for each client, and each client will load its individual data set in the federated learning uh, uh, server. So here we have this function which is called load dataset, and this function load dataset, it will load dataset for each client. When we look at client, the client.py script, it has an argument. It has an argument, and this argument, it will enable you to load dataset for each client. So we have so here we have the argument is called the client number. So we can pass this argument to load dataset for each client. So if let's say you have 10 clients, you can create 10 individual folders with each dataset for each client. And then you can just pass this argument with the client's number, and it will load that folder dataset for each client. After the federated learning is, so this is the load dataset. It will just load the datasets, and we have the evaluate function. So here it will, so here we load the images. So training and labeling images, that will be done by the server. And then here we have the evaluate function. So one of the things that I added here is after the federated learning has been done, the server will save the final model. And this is another cool thing with Flower is that here at the top, we are free to load any model. So if you want to load a MobileNet V2, if you want to load a YOLO V5 model, you are free. You can load it at this point. Same case here for the evaluate function. After the federated learning has been completed, the server will then save the model. So in this case, it will save the MobileNet V2 model in the saved model format. After saving the MobileNet V2 model, it will then test this model. Uh, After testing this model, we will use Edge Impulse Python SDK to profile the model and also to deploy it. And I will show this later. And that's basically it. So we have the server.py script, and this script basically it will initialize a model. After initializing a model, the clients will join to the federated learning server. Each client will train a model with their own data set. After the federated learning is complete, the federated learning server, it will save the model first, and then it will use Edge Impulse Python SDK to profile this model and then to deploy this model. I will talk about this profiling and deploying later. So what we can do to start this federated learning is we can run Python server, we can run the server.py script. So I will start the server script over here. And then here I have my, on my computer, I will start the client script. And remember, we have an argument client number that we can use to load a dataset for individual client. So in this case, I want my computer to be the first client. So I will pass the in client number argument, I will pass number 1 to specify that this is the first client and it will load the first folder. At the same time, here I have SSH to a Raspberry Pi. And here on the Raspberry Pi, I have the, So this is the Raspberry Pi. I have the client script and I also have the dataset folder. So this is the folders on the Raspberry Pi. So we have the client script and we have the dataset folder. So I will tell the Raspberry Pi to run the client script, and for the client number, I will pass the number to specify that this is the second client. And if you go to the server logs, we can see that the server, it has loaded the training images. It has initialized the model, and now it's waiting for the federated. And now this federated learning has been started. If both clients have connected, so my PC has already connected, and it's now training a mobile NP2 model. And if you go back to the Raspberry Pi is also training the model. Because of time, I will just skip this process because it will take quite some time for this uh, to finish. But I have some logs that we can look at um, regarding the processes. So here we have the server logs. So the server so this is the server. The server, it will initialize the initial uh, global parameters, and then it will evaluate the initial parameters for each federated learning count. So this is the first count. The server will um, aggregate the various model parameters that it has received from each client. And this will continue for 6 times that we defined in the client in the server.py script. If we look at these server logs, we can see that the model has an accuracy of 0.5. So this is initially, and then the accuracy goes up to 1. Um, One reason that will be the cause of this is in this case we are using a mobile NP2 model, and we are just doing a transfer learning. In this transfer learning, we want the mobile NP2 model to detect if there is a head or if there is a heart. Now these two images that we are showing the model, they are not very complicated model, they are not very complicated objects. So the mobile NP2 model, it may be learning easy for this particular task. That's why we can see that the accuracy, it's always 1, because it's not a very difficult task that we may be giving the mobile NP2 model. Finally, after the federated learning, the server will then save the model. So here we can see that the server has saved the model. And here on the folders, we can see that there is a saved models folder, which has a mobile NetB2 model over here. So this is one thing that the server does. So this is the final model that the server aggregated from both the Raspberry Pi and also PC. And the server will also test the uh, final model. So in this case, for the testing, we can see that the server, it tested the final model on an hard image. And the model actually predicted fine. It looked at one image and it correctly predicted that that was a hard image. And here we can see that the performance of the model is actually fine. Afterwards, the server then uses the Edge Impulse Python SDK, and here we can see this function for the profiling and deployment. So one thing when it comes to machine learning models, we want to know performance of the model. So in this case of IoT devices, not every model can run on any device. You can't take a YOLO V5 model, then maybe you run it on an Arduino. So one of the things that we can do with Edge Impulse is that we can actually profile this model. And by profiling means that we will get the performance of the model. So in this case, we profile the model for the Raspberry Pi 4. And we can see that the here we can see the performance of the model. Like the time per inference of this model is just 54 milliseconds, which is actually quite impressive. You can also see the RAM and also the um, ROM or the flash consumption of this model. Uh, using the profiling. And so the profiling, it enables you to get an overview of your model, which MCUs and also which computers can your model run on, and also the performance metrics of your model on these various devices. So here we can see the logs for profiling the final model for the Raspberry Pi. So the time by inference is 54 milliseconds. And here we can also see a performance on other devices. So like for the Cortex M0 devices running at 40 uh, megahertz, we can see that this model is actually supported for these devices. And the time per inference here is actually quite high because it's at 370 milliseconds. But again, we can optimize this model by maybe selecting uh, mobile, another model. So in, instead of maybe selecting MobileNet V2, we can select another model. Another thing that we can also do is, if you remember, we used an image size of 160 by 160. We can, let's say, reduce this image to, let's say, 48 pixels by 48 pixels or 96 pixels by 96 pixels so that our model can become less resource. Um, uh, it can consume less resources on the devices. So here we have logs for profiling on various devices. So here our model is supported on high-end MCUs. It's supported on accelerator boards like the Renesas boards, uh, the Renesas board, the NVIDIA board. So here we can see that it's supported there. It's also supported on MPUs like the Cortex A72. It also supported on GPU or MPU accelerators. Um, and we can see here, like for the GPU or MPU accelerators, the time per inference is just 9 milliseconds. And but if we see for the low end MCUs, we can see that the time per inference is 370 milliseconds. And we can relate to this performance because a high-end MCU means it has more resources to run our model, but a low-end MCU, it will struggle a bit. So that's why the inference time is actually quite high. Now, once the profiling is done, if we go back to Edge Impulse, uh, so if we go to Edge Impulse, we'll actually see our model. And one of the things that Edge Impulse recently added is bring your own model. So you can actually bring your own model to Edge Impulse. And this is actually one of the things that this project does. So the server, it will aggregate the final model. And then this final model, it will be sent to Edge Impulse. And here in Edge Impulse, if we go to upload your model, we can see that the model has been uploaded to a Gimbal. So what we can do here is we can do some configurations. Like here, the model, it's the model input. This is an image classification model, and it takes RGB images. The for the image processing, the pixels are not normalized, so we can select this. And the model output, this is an image classification model, so the output is a classification um, class, and the labels are head and hearted. The same things that we defined in the server script are the same ones that we select over here. And our model is now on Edge Impulse. So one of the things that we can do is if we come here and we give our model, let's say this image, we can test this model on uh, an image. So here I've given this model, this image. So this is an image of a person with a safety hat. And in our problem, this is a hard hat image. And we can see that our model has correctly predicted that this is a hard hat image. From there, we can further test our model. So on Edge Impulse, I have a couple of images that I have uploaded. that we will use for testing. So I can come here to data acquisition, test, and here we have a couple of images. So this is an image of a person with a hard hat, and the label or the class of this image is hard hat. So we can see another image of a person with just a head, and the label for this image is just head. So we can go to model testing, and then we can test all the images with this model at once by just clicking this button over here, and the model will be tested on these images. So initially, the model um, it achieved an accuracy of 93%, which is impressive. And from here, we can then go to the deployment. So one cool feature with Edge Impulse is that you can deploy your model to a wide range of devices. So we can, let's say, create libraries from our model. So Arduino libraries, C++ libraries, STM32 libraries, etc. We can also target various devices like the Arduino 33 BLE, Arduino Nicla, um, which other devices, Renesas, its studio boards, Sony boards, and such. In this case, I want to run the model on the Raspberry Pi. So on the Raspberry Pi, I have installed Edge Impulse for Linux, and I'm with Impulse for Linux. If we want to download a model from Edge Impulse, so what I can run is So what I can run is, so I can run this command to download our model. So this command, it will download our model from Edge Impulse as an EIM executable. And to explain what the EIM executable is on here on the Raspberry Pi, of SSH on the Raspberry Pi, I will run this command, Edge Impulse Linux runner, and then I will give it the model file. So if we look at this directory, we can see that there is this EIM executable over here. And I will run this EIM executable on this terminal. And right now the model is running on the Raspberry Pi. If I go to the Raspberry Pi here, so if I come here, I can see a feed of the Raspberry Pi. So here I can show the Raspberry Pi, let's say an image of a person. So here we can see that the Raspberry Pi is classifying that this image is actually a person's head. So I can show the Raspberry Pi another image. So like this one over here. And we can see that the Raspberry Pi is correctly classifying these images. I had a project over here, but Windows decided to do some updates, so I will use my phone to project. And basically, what the Edge Impulse Linux runner does is I have a Raspberry Pi over here with a camera, and so what's happening is that we are getting an image from the Raspberry Pi. We take that image, we process that image, and then we give this image to the model. And then finally, the model, it will also give us the output. So here we can see it's taking 38 milliseconds to classify this model, and you can see the predictions over here. And all of this is running just by running this command over here. So the executable here, it's called an EIM executable. And this executable, it has your signal processing and also your machine learning model in just one executable. And then using the Edge Impulse Linux, it enables us to get images from the Raspberry Pi camera, and then we pass these images to the machine learning executable, which will do the processing and also the classification. And then we will get this live stream from the Raspberry Pi over here. And so that is basically it when it comes to federated learning. So instead of taking all images and then putting it to one computer and then training the model over there, we can train the model on various computers. And then let's say we take the final model, we push it to cloud server like Edge Impulse, and then we can deploy this model to any device, provided it can run the model. And yeah, that's it from me.
That was really cool.
Questions?
Yeah, thank you so much. I really appreciate the depth that you went to there. I think people are going to love this tutorial, and I'm sure like a lot of people are going to end up watching and following up. Unfortunately, we're running a little bit low on time, so I can't really take questions right now. But I think what we can do is look for opportunities maybe through our Slack to collect a few questions and pass them along to you. If you, I'll follow up with you and think we can do it that way, because this is really great content I haven't seen anywhere else before, and so we're always super excited to bring that type of content to our folks. Thank you so much, Solomon. That was amazing. That was great. Well, with that, I'm going to shift gears and introduce our next speaker. To do that, I'm going to share my screen once more. And let me make sure I do this right. I think this looks clear. This is our next invited talk. We're going to conclude our Flower Monthly for October by diving into blockchain and seeing how that type of exciting technology can influence how we build federated learning applications. And to do that, we have a world-class expert in this space. His name is Kwangkee Lee. He is a principal investigator at an exciting organization called InnopiaTech. And I'm really delighted to have him here today and sort of pass along over to him to tell us all about it.
Okay, my name is Kwangkee Lee. I'm working for InnopiaTech in Korea. It's a company. Okay. So let's get started with the question of why BCFL is required. BCFL means blockchain-enabled federated learning. Some critics argue that blockchain and Web 3.0 are overly complex architecture for problems that do not exist. But the technologies and market landscape are rapidly evolving, and we are trying to find an answer. As we know, while FL technology has made significant advances, it still faces challenges such as single point of failure, malicious clients and false data, and the lack of incentives. Recently, blockchain has been widely identified as a potential solution to address the above-mentioned issues. The vanilla federated learning is based on a traditional client-server architecture, in which trustworthy central authority is needed for coordination. On the other hand, the real-world use cases of FL require untrusted settings that do not rely on a single central server and have to deal with dishonest clients effectively as well. So BCFL has an idea that blockchain is used as the underlying architecture for federated learning has gained traction lately and has become a rapidly evolving area of research and development. But for blockchain, there's a core problem that needs to be solved. The problem is well known as the blockchain trilemma. The blockchain trilemma states that it is impossible for a single blockchain network to satisfy all three characteristics at the same time. That means we can only meet two of the three possibilities. In fact, in integrating FL and blockchain, we have the same challenges in managing the trade-offs among the three desirable attributes. So a sort of compromise is needed in real-time deployment. And today I'd like to introduce our ideas and efforts to solve the trilemma in BCFL applications. It is worth mentioning that there are several design choices for integrating federated learning and blockchain features, each with its own pros and cons. One possible option is tightly coupled, in that the clients of FL are also nodes of blockchain. In other words, the clients that not only train the local models, but also verify the updates and generate new blocks. Another option is decoupled. In the case no node works in both systems. In the case the system consists of a blockchain subsystem and a federated learning subsystem. Considering that blockchain is still evolving, and so is federated learning, one of the most important questions to BCFL design would be if and how tightly FL and BC should be integrated. We believe that decoupled or at least loosely coupled integration is inevitable for real-world deployment. And considering FL still faces various technical challenges and in its early stage of industry adoption, flexibility and extensibility are important. In addition, we realize that great efforts are being made in the Flower community to make the FL real. So we intend to integrate tightly with Flower to observe and reflect the advances of FL in a timely manner. Based on the design choices mentioned before, we proposed the novel reference architecture for BCFL and implemented and verified it in an Ethereum development environment. One big difference of BCFL is that in traditional federated learning, the selection of local clients and aggregation of learning outcomes are performed under the control of the central server. But in BCFL, all of these processes are monitored and managed through the smart contract. Core ingredient of BCFL includes smart contract, IPFS, DID, and incentive reward mechanism, etc. They are all rooted in blockchain, Ethereum, and Web 3.0, but are defined and reused for BCFL. Next, let me explain how we integrate blockchain with Flower, which I believe we are the first. The principle of our implementation is to make BCFL compatible and interoperable with existing and evolving Flower framework. So no change in Flower framework structure and code is allowed. Thanks to the flexible Flower architecture, all we need to do is simple addition and extension to integrate BC with FL. As addressed in the Flower materials, even though the current implementation uses gRPC, we can add alternatives for communication and information delivery. In short, our proposal is to use IPFS, interplanetary file system, without any change in Flower framework. The difference is in our proposal, CID, content identifiers of the stored models in IPFS are delivered under the control of smart contract. That means in Flower, models are directly passed through the gRPC channel. On the other hand, in BCFL, model delivery happens via IPFS under the control of smart contract. No direct delivery of models between the server and client is happened. As you know, in Flower framework, client is the abstract base class for Flower clients. This means that abstraction of client defines a few abstract methods, such as get parameter, fit, and evaluate, that need to be implemented in the Flower client class. To reuse all the great features of Flower and make BCFL interoperable with Flower, we defined the abstract base class for BCFL clients called ith client, which has the same set of abstract methods of client. In addition, we have added a few more abstract methods that need to be implemented in BCFL client. For server side, we defined id server, which is inherited from Flower server. As a result, we can start the BCFL server as the same way Flower server is started. Furthermore, all the strategies of Flower is used without any changes of Flower framework code. Actually, we submitted a full request a while ago, but we have ideas for further improvement. So I'd like to discuss these points with the Flower community later. For now, we focused more on the verification of architecture rather than the FL performance analysis. However, due to our implementation strategy, we expect exactly the same performance and behavior as that of the Flower framework. Future directions. We will focus more on performance evaluations. And mainnet deployment is another important milestone for us. And actively following up on the progress of the Flower framework would be important for us. Especially fair and efficient contribution evaluation of the participating clients is critical to BCFL, but we know it is very challenging. As you know, there are several outstanding works for contribution evaluation out there, but we need more thorough and intensive comparison and evaluation from the perspective of complexity and performance. We have a long list of recently published works for BCFL, but again, I believe we are the first and only so far to integrate with Flower. For the plausible target application of BCFL, we are working on a platform for digital healthcare, especially for DCT, decentralized clinical trials. In our scenario, participants of clinical trials are rewarded as per their contribution to federated learning training. We also expect FLTM including BCFL to be useful for a more wide area of applications. Let me see some simple demonstration. The first thing is to publish the task with some characteristics of the models. And after that, the trainers will participate. First client is participating with the registration of their data. And second participant. as you see, the we use all the framework, flower framework. You can see the familiar flower framework log here. As the participants, all the clients are participating, the process is beginning. The FL training is in progress. I'd like to point out that the all the transaction is stored in the blockchain network, so we can scan and check the that transaction. That's the beauty of this one. That's the beauty of the blockchain characteristics. And this is the demonstration. The final model is NFTized, and then can be transferred to the marketplace, and the buyer and the seller can exchange their information to this demo. So we just completed some basic building blocks of the FLTM and the BCFL. Okay, that's it.
Perfect. I haven't seen a demonstration like this before, so it's really pretty interesting. I can take a few questions because you kind of stuck to the time budget quite well. Let me take a couple of them from the Slack in different places. Yes, I have one question where they're interested to know, what do you think the most what are they saying? I guess they want to know what's the key application you see being enabled by this sort of framework? What's the one that you're most excited by?
I suggested the kind of model marketplace is a kind of plausible application with this BCFL. So so to build a model, we need good data, and to give a reward and incentive is important to thing for the participants to contribute with their data. In our case, we are more. Our first target is kind of a digital healthcare scenario, but I think it is more widely. We have more wide application areas.
Oh, for sure. Yeah, I can see that there's a kind of wide diversity of applications one could build. I guess they were just curious about what you think is going to be the first mover. But I see the model marketplace, data marketplace makes a lot of sense. I'll take another look to see what we have here. If anyone else, I don't know, maybe if Julian or Javier have a question. Otherwise, I'll go to the pool. There's a question about I guess the different types of cryptocurrencies and so on, and there was some discussion about the speed of transaction and if that would be an issue for building one of these type of architectures. There's some discussion about Bitcoin and Ethereum. But do you think this is an issue, or would you, I don't know, I'm not familiar with the area, but would you build another token to build these systems, or would you build it on top of the existing blockchain? cryptocurrencies, or perhaps is the question a bit misguided in nature?
Each have different idea and strategies, but my first target is to deploy our technology to the existing blockchain networks, such as Ethereum and Ethereum compliant mainnet, such as we have Polygon and other mainnets that support scalability.
I see.
Having our own, building our own blockchain network is another option, but it could be very difficult, and it could be a very huge work. So
for sure, yes, I see. But I guess that there are also this issue of performance that comes up sometimes. If for the type of networks you're building on top of, is performance and the amount of transactions that can, or I guess in this case not transactions, but the amount of verifications and so on, that's not an issue, or
yeah, that's a as I mentioned, we have blockchain trilemma. The scalability is the real issue for any real world deployment. Especially blockchain is designed for simple transaction, but the artificial intelligence and BCF federated learning, if we have to record all the those kind of transaction, it would be a kind of huge, and network cannot endure that amount of traffics, and speed
right.
is not so so some we made some kind of compromise. So there are tens of hundreds of different BCFL architecture. They have their own idea to compromise the security, decentralization, and scalability. So I'd like to stress that our approach is unique because we rely on the Flower framework. Most of the core functions of federated learning is happening in the Flower framework side. So I'd like to suggest we more kind of discussion, and the would be helpful.
Well, yeah, I mean, along those lines, what would be a modification to the existing framework that would make your life easier, or maybe would enable you to build something even more powerful? What would be the number one on your wish list that either us or people in the community might build to kind of supplement what you're trying to drive towards?
We first believe that some kind of modification is necessary to support the model exchange through IPFS. But as I showed in my presentation, no kind of change is necessary. Just extension and the addition of the is enough to implement the BCFL, our architecture of BCFL. But as we go on, we may need. We can find some different idea.
I see. Understand. Well, I think those were the main questions I saw being asked. The most substantial ones.
I have one small question. Can I ask?
Oh yes, please go for it. Yes.
I think it was very interesting talk. I have just one probably very simple question. Does your solution or current solution rely on some particular hardware, or is entirely a software solution, and anyone that has whatever is needed to sign in the blockchain can participate?
No hardware dependency at all. No hardware, I think.
Okay, that's cool. I was checking Innopia website and saw some hardware components, so I thought maybe there is some hardware involved. But okay. Thanks.
Well, great. We have reached the end of Flower Monthly for October. That means we can look forward to Flower Monthly November. It is going to be on November 1st, unless I got something wrong with the calendar. November 1st, which is our normal routine of the first Wednesday of the month. It'll kick off at 1600 UTC, so we try to keep that time nice and consistent for folks. And if you're curious about this event, this monthly event, or any other events that we run in the community, you can subscribe to our calendar. You can see that easy to enter in URL on the screen here. You can join our Slack workspace if you want to be notified about events of this kind, or have the opportunity to ask questions and socialize with other people who are really into not just federated learning, but forms of privacy preserving learning, decentralized learning, or as we've seen today, blockchain and TinyML styles of machine learning. And we're also always happy to gather feedback. There's a special dedicated channel in our Slack called Flower Monthly to gather feedback about what you'd like to see moving forward in this format. And with that, I'd like to close proceedings by thanking very much Kwangkee Lee for his excellent talk on material I haven't really seen discussed or demoed in this fashion before, where you can bring together blockchain and federated learning technologies. I hear it spoken about a lot. People sort of throw it out there. They say, oh, can federated learning take off? Unless you've got some sort of blockchain-backed verification of the transactions. People say these words, but I never see the demos. And so today I saw the demo. So that's great. And then we also heard from Solomon Githu, who spoke to us about a tutorial he authored as part of a contributor to the Edge Impulse network of experts, of which he is one. And I really enjoyed the depth that he went into to kind of show us how you can use Edge Impulse tools with the Flower framework to stand up very easily, or relatively easily, once you know how, IoT-backed federated learning. So fantastic. I guess I want to thank everyone for joining us today, and you'll be seeing these recordings posted on YouTube later. Take care, and thank you again both to our invited speakers. Thank you so much.
Thank you very much.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Bye-bye.